Before diving into any line integral, ask one question first. Is there a faster route than brute force parametrizing? There are 3 shortcuts to check in this order. 1. Is the field conservative? If yes, skip the whole line integral, just find f, the potential function, then subtract its value at the start point from its value at the end point. 2. Is the curve a closed loop? If yes, Green's theorem may turn this into a much simpler double integral. 3. If neither applies, direct substitution is still fast. Parameterize, differentiate, dot the vectors, then integrate. Pattern to recognize. Always scan for these shortcuts first. The slowest method is only a fallback, never the first move. Question 1. Direct substitution, no shortcuts available. 5 separate fields and 5 separate curves, none conservative, none closed loops. So direct substitution is genuinely the fastest method here. Pattern to recognize. Whenever the curve is already given as r of t, skip straight to differentiating it. Don't waste time reparametrizing something you're handed for free. Part A. Field f equals x squared y, xy cubed. Curve r of t equals t cubed, root t, for t between 0 and 1. Step 1. Substitute the curve's components into the field. Step 2. Differentiate the curve to get r prime of t, which is 3t squared, 1 over 2 root t. Step 3. Dot the 2 vectors together. Step 4. Integrate from 0 to 1. Answer: 79 over 190, approximately 0.416. Part B. Field f equals square root of 2xy, sine of y. Curve is the parabola y equals 2x squared with x between 0 and 1. Pattern to recognize. Since y is already given in terms of x, let x itself be the parameter t. Don't invent a new letter. Substitute, differentiate, dot, and integrate from 0 to 1. Answer: 9/5 minus cosine of 2, approximately 2.216. Part C. Field f equals cosine x, xz, sin z, a 3-dimensional field. Curve r of t equals t squared, 2t, t cubed for t between 0 and 1. Same 4 steps, but take extra care on the xz term. Make sure both x and z are replaced by their t expressions before multiplying. Differentiate, dot, and integrate from 0 to 1. Answer: 4/3 minus cosine of 1 plus sine of 1, approximately 1.635. Part D. Field f equals x squared y, y cubed. Curve r of t equals cosine t, sine t, for t between 0 and pi over 2. Pattern to recognize. Cosine sine parameterizations almost always produce trig identities worth spotting before integrating. Watch for double angle simplifications. Differentiate, dot, and integrate. Answer: 1/4 minus pi over 16, approximately 0.0537. Part E. Field f equals e to the 2x, x squared y. Curve r of t equals t squared, negative t cubed, for t between 0 and 1. Same method throughout. This one is pure careful execution, no special trick. Differentiate, dot, and integrate from 0 to 1. Answer: e squared over 2 minus 1/5, approximately 3.495. Question 2. Spot the conservative field and skip the line integral entirely. Every field in this question is secretly the gradient of a hidden potential function f. Once you find f, the actual shape of the curve becomes irrelevant. The fastest method is always confirm it's conservative, find f, then just plug in the 2 endpoints. Part A. The potential is f equals y times e to the 2x, so the field is 2y e to the 2x e to the 2x. Evaluate along a semicircle of radius 1 from negative 1, 0 to 1, 0. This is the clearest example of the shortcut's power. The path looks intimidating to parameterize directly, but once f is found, the curve's shape never even enters the calculation. Compute f at the endpoint minus f at the start point. F of 1, 0, minus f of negative 1, 0, equals 0 minus 0. Answer: 0. Part B. The potential is f equals x cubed y cubed, so the field is 3x squared y cubed, 3x cubed y squared from 0, 0 to 1, 1. Compute f at 1, 1 minus f at 0, 0, that's 1 minus 0. Answer 1. Part C, the potential is f equals root x plus root y, so the field is 1 over 2 root x, 1 over 2 root y, from 1, 1 to 4, 9. Compute f at 4, 9, minus f at 1, 1, that's 2 plus 3 minus 1 plus 1, which is 5 minus 2. Answer 3. Part D, the potential is f equals xyz, so the field is yz, xz, xy, from 0, 0, 0 to 1, 2, 3. Compute f at 1, 2, 3, minus f at 0, 0, 0, that's 6 minus 0. Answer 6. Part A, the potential is f equals e to the x sin y, so the field is e to the x sin y, e to the x cosine y, from 0, 0 to 1, pi over 2. Compute f at 1, pi over 2, minus f at 0, 0, that's e times 1, minus 1 times 0. Answer, E approximately 2.718. Question 3, working backwards from a target answer. Here the landscape f of x, y equals x squared plus y is given directly. Since the field is conservative, the answer only depends on two numbers, the value of f at the start and the value of f at the end. The path in between is completely free to choose. Part A, target answer of 2. Pick a starting point where f is convenient. Say 0, 0, so f equals 0. Pick an ending point where f is exactly 2 more. Say 1, 1, so f equals 1 squared plus 1, which is 2. Then f of 1, 1, minus f of 0, 0 equals 2 minus 0. Answer 2. Part B, target answer of 0. Pattern to recognize. The easiest way to force 0 is picking a start and an end point where f gives the exact same value, even if the points themselves are different. Try start 2, 0, and end 0. 4, f of 2, 0, equals 2 squared plus 0, which is 4, and f of 0, 4, equals 0 squared plus 4, which is also 4. So the difference is 4 minus 4. Answer, 0. Question 4, when the shortcut secretly fails. The field f equals negative y over, open bracket, x squared plus y squared, close bracket, x over, open bracket, x squared plus y squared, close bracket, spins around the origin like a whirlpool, and it's completely undefined exactly at the origin, a hole in its domain. Step 1. Compute the curl directly. It works out to 0 everywhere the field is actually defined, away from the origin. Step 2. Despite curl equaling 0, deliberately test two different paths between the same 2 points, 1, 0, and negative 1, 0. Path A. The upper semicircle through 0, 1, the integral works out to pi. Path B. The lower semicircle through 0, negative 1, the integral works out to negative pi. Step 3. Pi does not equal negative pi, so the two paths give different answers. Path independence fails here, even though curl equals 0. Step 4. Here's why. The domain has a singularity right at the origin, so the guarantee that curl 0 implies path independent everywhere does not apply. One hole in the domain is enough to break the shortcut. Question 5. Closed loops, with Green's theorem as the default first move, not a fallback. Every part here is a closed loop, which immediately means Green's theorem should be your first instinct. Convert to a double integral first, and only fall back to direct parametrization if that double integral looks harder than the original. Part A, triangle boundary with corners 0, 0, then 1, 0, then 0, 1. Here p equals y, and q equals x squared. Step 1. Find curly dq by curly dx minus curly dp by curly dy. That's 2x minus 1. Step 2. Set up the double integral over the triangle, using its slanted edge as one of the limits. Step 3. Integrate the inner variable, then the outer variable. Answer, negative 1/6. Part B. Unit circle boundary, with p equals negative y and q equals x. Pattern to recognize. A circular boundary means you should switch to polar coordinates immediately after applying Green's theorem. This is almost always the fastest route. Here, curly dq by curly dx minus curly dp by curly dy equals 2, so the double integral is just twice the area of the unit disk. Answer, 2 pi. Part C. Rectangle boundary from 0, 0 to 2, 3 with p equals xy squared and q equals x squared y. Step 1. Find curly dq by curly dx minus curly dp by curly dy. Before setting up any integral at all, the x derivative of x squared y is 2xy, and the y derivative of xy squared is also 2xy. So they cancel exactly to 0. Pattern to recognize. If this difference comes out to 0 immediately, the entire double integral vanishes, no matter the shape of the region. Answer 0. Part D. Triangle with corners 0, 0, then 2, 0, then 0, 2. Here p equals xy plus sine of open bracket x plus y close bracket, and q equals x squared plus sine of open bracket x plus y close bracket. Step 1. Apply Green's theorem regardless of how messy p and q look. Subtracting the two partial derivatives makes the sign of x plus y. Terms cancel exactly, leaving just 2x minus x, which is x. Step 2. Set up the double integral over the triangle's actual boundary, integrating over whichever variable makes the slanted edge easiest. Step 3. Integrate inner, then outer. Answer 4/3.